Hi, my name is Scott Simpson, and today we're going to talk about molecular orbital theory as it's applied to a homonuclear diatomic molecule. So homonuclear meaning the same atom, diatomic meaning two atoms, and of course molecule, a collection of atoms. Okay. We're going to consider the MO diagram. For N2, nitrogen. So we have to consider the different types of interactions we're going to have. We're going to draw our MO diagram. On this side, we're going to draw pictures of orbitals and the type of overlap we have on this side. So if you're working on a sheet of paper, just be sure to leave yourself a little space. Okay, if we write out the electron configuration for N2, we have our 1s, for nitrogen, then we have a 2s, draw that a little bit better, and 2p, and then we will also have another nitrogen fragment, and we want to make sure these orbitals are at the same energy. Perfect. Okay, we've seen the overlap between s orbitals before. We know we're going to make sigma type interactions. Oh, we should fill in our electrons first though. Oops, forgot one. So, with the 1s orbitals, there's going to be some overlap. We're going to get a sigma bonding and a sigma anti-bonding. Should be a little more symmetric in the center. We'll try that again. Oops. We get a sigma star. We need to keep track of those symmetry labels again. We know that this one's a G and that one's a U. Okay? 2s, same sort of thing. The dispersion will actually be different, but we'll leave it this way for now. The thing that irritated me when I was a student starting out doing this, I didn't know how these energies were calculated. They're actually done quantum mechanically through all sorts of theoretical methods like Hartree-Fock, density functional theory, and so on. But I was always amazed that my professors knew where these energy levels lined up. The reason they knew was either from a quantum chemical calculation or just prior experience or knowledge that they've had in the past. So, let's put symmetry labels on this guy. This guy's G, this guy's U. Now, let's think about the overlap that will happen between p orbitals. So, let's consider we have three sets of p orbitals. We're going to draw two of them. We'll call this one the px. So this is on nitrogen 1. That's on nitrogen 2. So let's call that the px. There's two types of overlap we could have here. We could have it where that's going on, or like that. Now, even though these two, if we were to consider the wave function or the molecular orbital, there would be no sign change between these two basis functions or these two orbitals, and they'd actually be in phase with one another. However, if you look at the overlap that we have is destructive. These two overlap and it's destructive interference. This is actually an anti-bonding sigma. This is a sigma star, whereas this guy is a sigma. There's overlap just in one region. These two functions have the same sign, so there's going to be constructive overlap. If we allow the orbitals to mix with one another, 'center. Let's try to draw orbitals that should happen. So there's constructive overlap, between these two atoms. There should be a negative charge filled in there. And then we have our positive lobes. Then for the top one, there should be a node right in the dead center. There's going to be destructive overlap along that way. And what we'll get should look like this. Now we have to give our symmetry, or our MO symmetry labels. We have U and G. Remember, G is symmetric due to an inversion, where U is anti-symmetric to inversion. If we look at the inversion center right here in the dead center, we can see that this system does indeed have symmetry with respect to inversion, so we would give this guy a label of G. If we look at our MO up top for the anti-bonding, we'll see that's at U. So those are the two p orbitals that are pointing directly at one another, but what about the others? We have the pz and we have the py that are pointing this way. What type of overlap are they going to have? Oh, first we'll draw these two guys. Whoa, wait a minute. Now let's consider pz orbitals. Should have gave myself a little bit more space. We're going to erase this. So we have pz. Another pz. We can have where there's no sign change between the two, and then we can have where there is sign change between the two. If we look at the type of overlap we're going to have here, it's going to be in two regions. So these are actually pi orbitals. There's constructive overlap between these two lobes and these two lobes. So this is going to be the pi bonding, where this guy is actually going to be the pi star or the pi anti-bonding. If we allow these orbitals to mix and we look at their overlap, we should get an orbital that looks like this. Nope. There are two nodes there. Then when we consider a p orbital, we get something that looks like that, where there's one orbital cutting through, or excuse me, one node cutting through the center. Now we have to determine if these guys are symmetric or anti-symmetric with respect to inversion. If we plunk right in the center, this guy actually is symmetric with respect to inversion. So the pi star would get a label of G, whereas the pi bonding, if we look at that, it's not symmetric. If we put a symmetry operation of I here, this positive lobe would become negative, that negative lobe would become positive, and it's not symmetric. So this gets a U. All right, but we've only drawn the px, which are pointing at one another, and the pz. The py is actually doing this exact same thing as the pz, except it's extending out towards us in the board. And that's a little more difficult to visualize. So, but it is doing almost the exact same thing here. So if we go over to draw our molecular orbital diagram, we have to keep things in mind. What has the best quality of overlap, sigma or pi? And it's sigma that has a better quality of overlap generally. So we should label our sigma star, and we have to have the proper symmetry labels there. We're going to have G and U yet again. Okay. But what about the pi orbitals? Now the pi orbitals, they have less dispersion. Their overlap is worse than that of a sigma bond. And since we have the pz and the py, there should be two pi orbitals and two anti-bonding pi orbitals. Now if we give those the proper symmetry labels. Remember, in this case, the bonding has a U and the anti-bonding has a G. We proved that over there in terms of the symmetric case. Now, we have a total of 2, 4, 5, 6, 7, 14 electrons in total. Let's start to fill this. We start with the lowest energy molecular orbital and work our way up. So we got a total of 8 right now, 10, 11, 12, 13, 14. Okay. So now, that's for N2. If you calculate the bond order of the system, which we can do really quick, equal to 1/2 number of electrons in bonding orbitals. Let's count them up. 2, 4, 6, 8, 10. Minus number of electrons in anti-bonding orbitals. 2, 4. We get 10 minus 4, a total of 6 over 2, or 3. So what does that mean for us? That means there's a triple bond between these two nitrogens. So, if we go to draw that out, we get NN, like that. And that matches pretty well with the Lewis structure. Okay. There is one more thing we need to discuss when we're talking about homonuclear atoms, and that is orbital mixing. So if you look at some of the earlier elements, diatomic molecules in this row, what you'll see is that sigma G and that sigma U switch spots. Why does that happen? It has to deal with the symmetry of these orbitals and the orbitals themselves, the molecular orbitals, interacting with one another. So let's discuss orbital mixing. So orbital mixing. So MOs of the same symmetry can interact. The lower in energy MO mixes with a higher energy MO, and it results in that lower energy MO becoming even lower in energy. Well, the opposite happens for that higher in energy orbital. So lower energy MO gets lower in energy, whereas the higher energy MO gets higher. In energy. So, we're going to draw two systems. We're just going to consider a set of 2s and 2p orbitals interacting with one another. We're going to look at it where we don't allow the MOs to mix and where we do allow the MOs to mix. So in this case, this is not mixing. So we got that 2s, that 2p. Then we allow them to mix, and this will be with mixing. Okay. So in our general case, what would end up happening? We get a sigma G, sigma U star. The p orbitals overlap, and it's going to look very similar to that of the last MO diagram that we drew. So we got sigma G, oops, not star. Sigma U star, we got pi star G, pi U. Okay, and we want to circle orbitals that are going to interact with one another, ones that have the same symmetry. Sounded terrible. That sigma g orbital that's resulting from the overlap of these two s orbitals is going to interact with the sigma g orbital that results from the two p's. This sigma u star is going to interact with the sigma u star that results from the interaction of the two p orbitals. And these these pi orbitals are left alone because there's no other orbitals in this system for them to mix with. If we do that, we said these lower in energy orbitals get even lower in energy. So they've been exaggerated a bit. Whereas this sigma g orbital, it should raise in energy, and in some cases it actually rises above that pi bonding set of orbitals. So we try to draw that as best as we can. Sigma g, pi star g, and this one raises up even higher in energy, sigma u star. So that is what is meant by orbital mixing, and depending on what part or how the quality of overlap is between the atoms, you might get an MO diagram that is better represented this way rather than this side. This is more true for the earlier elements in that row, like when we're considering nitrogen, and these are for the later ones. Okay. So with that, I'd like to thank you. The next video will be on heteronuclear diatomic diatomic molecules. But if you have any questions about this, please leave any comments or concerns below. And thank you for watching.